Thanks for the introduction. I feel really blessed to be able to give the talk in person today. The state of the last few is quite sad. Also, yeah, I'm not talking about any work that I've done at Roblox today, but if you'd like to ask me about game engines, I'm happy to chat about them afterwards. This is work that I did during my PhD with my advisor, Alex Snoeren, on disaggregated cuckoo hashing. For anyone that was in this room yesterday listening to Anil's talk, this slide will probably ring a bell. The price per byte of storage has stagnated over the last 15 years. And this has led systems architects to trend towards newer disaggregated architectures. What is it that makes a device disaggregatable? Well, I would argue that it's that device's access time relative to its network latency that makes it a disaggregation success story. So with respect to RDMA, which is a popular transport, the intra-rack round trip time is approximately 2 microseconds. And if we look at that latency relative to storage devices like spinning disks and solid state drives, the value is less than 1%. And in these cases, they're relatively easy to disaggregate. But as we go to faster and faster media, like, for example, DRAM, that overhead is approximately 20x. And in general, I would say that the bandwidth is close to sufficient, but because of this inflated latency, the latency becomes the critical issue. When I'm talking about disaggregation, what do I mean? I'm really talking about the separation of a CPU from the resources that would normally be within a single box. And I have an example here on the right of a disaggregated rack where we have compute, memory, and storage, each in their own 1U servers interconnected by a fast 100 gigabit per second plus network. And the proposed advantages of this architecture are expanded per core capacity, decreased resource stranding, and the ability to flexibly upgrade and expand your server. I have a quick example here to just illustrate those advantages. So on the left, there's a monolithic server where all of the resources are in a single box, and I've highlighted their utilizations in darker color. So the higher up it is, the higher the utilization. And what I want to show in this example is that this blue machine is out of memory, where the red machine still has some left over. And so from the perspective of somebody who's bought these machines and actually purchased all of this DRAM, they probably bought enough, but it wasn't sufficient for whatever workloads they were running. And disaggregation aims to solve this by providing a vertical cut of these resources. So in this case, the red machine gets one less unit, the blue machine gets more, and in aggregate, we're able to even supply another machine, this purple one. There's a ton of work on this, and they usually do their work at the virtual memory interface in the form of a paging system. A lot of very successful projects here. But one thing that they usually miss out on is the ability to share. That's what I'm going to be talking about today, is how do we work towards extending the virtual memory interface towards a more sharing capable system. Sharing disaggregated memory is really hard. You heard about this in the prior talk, and it's hard for really two main reasons: contention and failures. Contention makes sharing really difficult because when you have multiple readers and writers to the same data, they can invalidate their local caches, and the cost of synchronizing these caches become very high, like when you're spinning on a lock. Simultaneously, the costs of failures are very high because you need to have these complicated protocols for recovering from failures. Key value interfaces are one of the most successful at dealing with this problem by abstracting away byte addressable memory with interfaces like put and get, which can handle these behind a separate protocol. And in the development of these protocols, making them fast is really the key problem. So reducing the number of round trips and implementing these protocols using just one-sided RDMA operations. And that's what I'm going to be talking about today, is like how we can take steps forward towards minimizing the number of round trips. Fundamentally, this is a data structures and algorithms problem. A lot of the data structures that you'll see in this space use sparse pointer-based structures, but there's also dense direct addressing. The advantage of sparse structures is that they're more amenable to optimistic concurrency, which means that if there's no real contention, you can get away without the cost of synchronization in most cases. And they also provide an easier mechanism for fault tolerance. So writers can do their work out of space, and then it can be committed using like an RDMA compare and swap atomically. But this indirection has a cost. Traversing pointers in remote memory requires multiple round trips, and this often leads to common case implementations where the round trips escalate. In contrast, dense structures can be indexed using a single round trip, but they incur additional complexity. So the moment that you have multiple clients, each accessing shared memory, you need locks to guard access to them. And also, you need to guard against failures. So if there's a partial write that's been done, you need to protect your data integrity with CRCs and recovery mechanisms. In prior RDMA literature, using two-sided RDMA, hopscotch hashing and cuckoo hashing showed really good promise. And the reason for this is that they support very fast reads and relatively uncomplicated updates and deletes. In the case of hopscotch hashing, they provide a locality parameter where you're guaranteed that the data that you're looking for is going to be within some bound h. And in the case of cuckoo hashing, it's going to be in one of two locations. So what this enables is that reads can be done asynchronously in a single round trip, and that in the case of updates and deletes, it's relatively easy to lock the data that you want to lock, perform the update, and get an answer back. Both of these protocols push almost all of their complexity into insertions. In the case of hopscotch hashing, they have inlined metadata, which needs to be maintained and updated on every insertion. And in the case of cuckoo hashing, collisions result in random searches throughout the table. So there's effectively no locality. And so in both of these cases, implementing these data structures using one-sided RDMA results in very complicated locking, complicated concurrency, and really difficult failure cases. Okay, so I have a straw man example here that illustrates how we could take cuckoo hashing and effectively get that same locality benefit of hopscotch hashing without additional complexity. So the idea is that the first hash location that you would hash to is just a uniform random hash, h of x. And then the second location is the first plus a second uniform random hash modulo that locality parameter h. And that's actually it. Just using this alone, you get those properties out, but this isn't really the best idea. So the moment that you start doing this, as a side effect of the birthday paradox, you run into collisions in the hash table very quickly. And you can't really recover from this. You need to resize your table and make it bigger. And this is actually like a really bad idea. The fill factors that you get in these hash tables are like 10 to 15%. So it's really awful. We almost stopped the project when we got that first result. But there's alternatives. So rather than this, what if we did something a little bit smarter and used a distribution where the median value of the distribution was that value h? And so there's a potential that rather than running into these very tight collisions, you might be able to escape. And that's actually sufficient. Without really too much more than that, we're able to get much better fill factors of up to 90%. This is one of the first contributions of this work, and so I'm going to talk about it for the next few minutes. So we call this idea locality hashing, and it's very similar to the ideas of how a skip list works. The idea is that you have logarithmically few keys in the table that point to exponentially far distances away. And in this example, we have keys like cat that have a pointer all the way to the other side of the table. But the majority of the keys, like dad, get, and try, only have a distance of 1 to their neighbors. And this is reflected in this cuckoo hash, which we call our cuckoo, where cat, again, points to the other side of the table, but there's a lot of keys that just point to their neighbors. And so what this means is that if we're trying to read this data, if we want to try and read try, we can locally determine that it'll be in one of two locations, many of which will be highly localized, and just read these 4 blocks, and we're guaranteed to find the data that we want. The formula for this that we're using is not that much more complicated than what you saw on the prior slides. The first location that we hash to is just a uniform random hash location. And the second one is the first plus a second uniform random hash modulo our exponential function. And this exponential function might look fancy, but it's really not that complicated. There's a constant f that we spend a lot of time discussing in the paper, raised to a function that just counts the trailing zeros of the hash. So that's going to grow logarithmically fast, and we raise it to the exponential. To illustrate the benefits of this, I'm just going to step through what traditional cuckoo hashing would look like in the form of an insertion with a collision, and then I'm going to show you the advantages that you would get from locality. So in this top cuckoo hash with independent hashing, this value pit is going to be inserted and collide with cat and dad. And from the client's perspective, it can acquire the lock ahead of time. It can perform a read at the same time as that lock. But after that, after it's had a collision, it now needs to make a decision about the next lock to grab. And this is going to be where recursive round trips come in. So the client needs to make a decision. It can go to the alternative location for cat. It can go to the alternative location for dad. And in this case, it's chosen cat and grabbed that secondary lock. And in this case, it's lucky. There's a location that it can actually insert into. But you can see that the process here, iteratively grabbing locks that go to random locations, can lead to deadlocks. It's an unbounded amount of time. You can get huge tail latencies. Now, in the alternative case, we can kind of get artificially lucky. So if we do that same insertion and we hit dad and cat, well, cat hashes to the other side of the table, so we could go chase that down. Or with high probability, dad will have a close hash location, which in this case is covered by the lock that we already acquired. So we don't need to do any additional locking. We can just perform our insertion. I have a CDF that shows what the expected distance in terms of span of the table is when we're performing insertions. So both dependent and independent hashing, up until a little over 50% of the number of insertions that we do, they don't collide with anything. You can just insert them right away, so their distance is 0, or 1 in this case. And in the independent case, after you break off of that, they start to essentially randomly span the entire table. But in the case of dependent hashing, it tails off much more slowly. And so 95% of the insertions in the dependent case fall within 32 rows. And in 99% of the cases, it falls within 256 rows. What this means is that we can just size our locks correctly to ensure that we only have to get 1, or maybe in the worst case, about 2 locks to perform an insertion. We really do get a lot of locality, and if you take the time to read the paper, you'll see that a lot of the optimizations that we get are essentially a fallout of generating this locality through hashing. We're able to develop a very fast on-NIC lock table and use masked compare and swaps to set all of the locks that we need to in a single round trip in, I believe, 99.9% of cases. But the real advantage for us is that we get to just take advantage of cuckoo hashing the way that it was intended to be used, which is that we can do things like inline data directly in the hash table to support very fast reads and writes. I have here just a part of our evaluation that shows us on a contended workload with 100% reads, 95% reads, and 5% writes, and then like a mixed 50-50 workload. And what I'd like to talk about is the advantages that we have over other disaggregated key value stores on this mixed read and write workload. So in this case, our reads are all going to be a single round trip, even though we're incurring writes on those same keys frequently. In the cases of the other key value stores, They're all pointer-based, so they require these additional round trips and traversals. But in our case, it's all in place. I think that potentially the most intellectually stimulating part of this work is the fault tolerance protocol that we put together. The moment that you start working with locks, you run into the situation where clients can fail while holding locks. And if you're using just one-sided RDMA, this is actually a very tricky situation to recover from. Using a really interesting mixture of RDMA protections, CRCs, and the way that cuckoo-hashing insertion works, we enumerated the number of failure cases that we could walk into and enabled a protocol where running clients can reacquire the locks of failed clients, ensure that they don't corrupt the table, finish the insertions that they were doing, and then repair the table back to a consistent state. And we're able to do this with a relatively high degree of parallelism as well. So on the right here, I have an example of us running a 95% read, 5% write workload, where we're increasing the number of client failures while holding locks as our control. And what you can see is that the number of operations that we're able to support per second start to drop pretty rapidly, but it's still able to support millions of operations per second because we're able to read, and only when we notice corruption do we stop to try to repair it. The numbers that we aimed for in this evaluation were pretty much the max number of RDMA failures you could have per second. We just tuned it to the max number of new RDMA connections that you could start per second. Yeah. So in summary, this is, we developed a high-performance cuckoo-hashing algorithm for disaggregated memory. It performs really well on read-heavy, write-a-little-bit workloads, and we developed a novel fault tolerance protocol for it. It's available on GitHub, and I'm happy to take any questions for it now.